All right, so today we're going to learn how to solve linear programming problems. So in this first example, we have a fairly abstract problem. We're just given the linear programming equations already set up. So we stripped away all of the context. We have it all formulated. We have some objective function, p of xy is equal to 3x plus 2y. We have to assume that's probably profit. We want to maximize it. And then we have some constraint equations. All right. And we're going to try and solve this problem. So the first thing I'm going to do is I'm going to graph these constraint equations because I know that I'm limited. My x and y values are limited by these constraint equations. So if I can first just narrow down the possibilities to the x and y values that satisfy these constraint equations, that's a good start. So let's start with that. All right, so I can't really get this all on here, but yeah, that's good enough. All right, so I have these constraint equations, and I'm just going to graph them to start out with. So probably the easiest thing to do would just be to plot the x and y intercepts and then shade the region that corresponds to these constraint equations. All right, so the first thing I'm going to do is just set up a little table of values. And the easiest thing to do would probably just find the x and y intercepts and then connect them with a line. But you know what I'm going to do first? I'm going to actually change colors because I'm going to make this red. All right, I'll make this my red line. All right, so x and y. All right, so when x is equal to 0, I get the y-intercept. So if I just plug x equals 0 in, this 2x term goes away. I just have 3y equals 12. So when x is equal to 0, y is equal to 4, and that's my y-intercept. So I'm going to plot that point. And then, let's see, then I'm going to look for the x-intercept as well. So that happens when y is equal to 0. I put 0 in for y. I end up with just 2x equals 12, and so the x-intercept is 6. All right, so I'm going to plot that point. And then I'm going to graph the line. All right, so I'm going to graph the line between these 2 points. So I'm just freehanding it here. So it's that's a pretty decent line, I guess. All right, so that takes care of the first line. Now let's see. I'm going to change colors. I'm going to make the other line blue. All right, so again, I'm just going to do the same thing. I'm going to find the x and y intercepts if I can. So I'm just going to create a little table of values. And when x is equal to 0, then it just becomes y is 8, right? So then the y-intercept is 8. And when y is equal to 0, I get the x-intercept. So then I end up with 2x equals 8. So x is equal to 4. Okay, so those are the values that correspond with that second constraint equation. All right, so I have 0, 8 and 4, 0. All right, and I'm just going to connect those two with a line. Let's see how well I can do. Okay. All right, I'm freehanding it, so, it's a little wobbly, but that's okay. All right, so now I have the first two equations graphed. Now, I should probably draw some arrows just to indicate which sides of the line the points that I want are on. And so you can see that if I put in 0, 0, it looks like that satisfies the equation. So I want things to the left of this line. And then same way with this one. So it's a less than equation. If I plug in 0, 0, 0 is less than 8. So it looks like I want things that are below this line. Okay. Now I also want x and y to be greater than 0, right? So I'm going to have I'm going to be shading things above the x-axis and to the right of the y-axis. And so the values that are that actually satisfy these constraints are in this nice little polygonal region here. So I'm going to shade that in. Okay, so there's my shading. All right. So that narrows down the possibilities to just that little region. Okay, those are my possible values of x and y, and we call that the feasible region. So let me scroll ahead here. The feasible region, the feasible region is the set of all x and y values that satisfy the constraints. All right, so once we found the feasible region, we got the set of x and y values narrowed down, we're going to use this first theorem that says that in a linear programming problem, the solution, if it has a solution, that it must occur at a vertex or corner of the feasible region. And hopefully that'll make sense. I'm going to try to show you a little demonstration here in a minute that'll hopefully help you understand why that's true, because it is really understandable if you think about it visually. So and so that's basically it. There's some caveats in here, but essentially we're going to just test the vertices. We're going to test the corners of the feasible region, and whichever one gives us the maximizes or minimizes whatever we're trying to do with the objective function, that's our solution. Okay. Now the second theorem just has to do with the existence of a solution. We'll get into that in a minute, but the method for solving a linear programming problem is called this method of corners. Okay, so we first of all graph the feasible set, which we already did, and then we find the coordinates of the corners of the feasible set. All right, and evaluate the objective function at each corner, and then find the vertex that either maximizes or minimizes the objective function. Okay, which is what we're trying to do. But really it comes down to that we just have to test the corners. Now, I never feel quite comfortable just giving you an algorithm and telling you, okay, do this and you'll get an answer. I really want you to understand what we're doing here. So what I've done here in GeoGebra is graph our feasible region, right? I've taken the two objective functions and the fact that x and y are greater than 0, and this red region is our feasible region. But I've plotted it in 3 dimensions. You can't really tell right now, but I've plotted this thing in 3 dimensions. And what I want to show you is that you can visualize the objective function in the 3rd dimension. It's as if the profit, so if our objective is to maximize profit, then we can maximize, or we can visualize the profit as another variable, as a variable in the 3rd dimension. So I've actually graphed this in 3 dimensions. All right, so there's our feasible set, and if I twist this a little bit, let's see if I can get this to work. Try to get it to. Sometimes it doesn't always do what I want. Okay, so if I twist this a little bit, you can see that I've got 3 dimensions here. All right, so you can see now the XY plane laying down, and the Z axis, which is our profit axis, sticking up here. All right, now I'm going to graph the profit function in 3 dimensions. So remember, the profit function is dependent on x and y, and if we know x and y, then we can just plug it into the profit function and get a value. All right, and that value will be the distance above the xy plane. So let me show you the profit function. All right, so that it looks a little hazy right now, but if I twist this again, hopefully you can see that the profit function is a plane in the 3rd dimension. Okay, so that's my profit function, and that plane is just, a distance above the xy axis. Okay, so you see that? Okay, now I'm going to turn on some points here. All right, now I'm going to take some point that I can move around. I could get this point that I can now move around inside my feasible region. All right, so I'm just going to park it here for a minute. And I've got a line that's going to go straight up. It's going to go straight up out of the xy plane, and it's going to intersect the profit function, that plane in the 3rd dimension. All right, now let's see where that profit function intersects the plane. Okay, so you see I have this point. Right now I've parked my point in the feasible region at 2.5. So x is 2.5, y is 1. And the profit corresponding to that that point in the feasible region is 9.5. Okay, the p, that's my p of xy. All right, and I can then now just move this around, move this point around within my feasible region, and I can figure out what the profit is at any point. Okay, so like if I go here, where x is 3.5, y is 0.5, then my profit is 11.5. Okay? And so let's see here. I can turn it around so you can kind of see what's happening here. All right, I'm just going to move that around. Now, I normally do this demonstration with a physical piece of foam board that I have cut out so that I can actually show you the slice of the profit function with everything stripped away except for the feasible values. But I think with this, what I can do is just move it to the corners, right? And we can kind of look at what's happening. So, oops, hang on. So I can, like, if I move it to this corner, right? This is one of the corners of my feasible set where x is 0 and y is, x is 4 and y is 0. You can see that the profit is 12. The p of x function, p of xy, is 12. If I move it along the line here, you can see, oh, it's going up. Look at that. My profit's going up. It's going up. It's going up. And when I get to this corner, now my profit is 13. So x is 3, y is 2, and the profit is 13. Okay, and I can move it along this edge. Uh-oh, now my profit's going down, right? So if I move it to this corner, this corner, it's x is 0, y is 8, or y is 4, and I have a profit of 8. Okay, and then I can also move it along this edge here. And so if you visualize, you could kind of visualize this. I wish I could had a better way of doing this virtually, but you can imagine that this that really I'm just dealing with a piece of this profit function plane. I'm not dealing with the whole plane, and so it's going to be like a three-dimensional shape, or sorry, not a three-dimensional. It's going to be a polygon, and the polygon is going to have edges, right? So so it would make sense that the profit, one of the corners is always going to stick up above any of the other values if I've just got this shape in three-dimensional space. Okay, so I don't know. This is my best way that I think I've found to do it virtually, but you can see that as I move along the edges, my profit function goes up to a maximum of 13, right? And then I've moved back along this edge. Okay, now my profit's 8. If I move down here, you can see at 0, 0. Okay, my profit's 0. Well, that makes sense. If I don't produce anything, I'm not going to make any money. And then anything in the middle here is going to be less than that maximum I found here at 13. All right, so let's go back to this boring two-dimensional system here that we have. And I just want to apply the method of corners. So what I'm going to do is find all of these points. Now, I already know some of these points, right? This is the point 0, 4. This is the point 0, 0, right? We're just finding the corners of our feasible region. This is the point 4, 0. Okay. And the only point that we don't know is this corner right here, which is the intersection of these two lines. So that's what I have to do first, is find the intersection. Find the intersection. Okay, and it's the intersection of the red line and the blue line. Okay, so I know my equations are 2x plus 3y equals 12. And the other one is 2x plus y equals 8. All right, those just the equations of the line, right? That's where they're where it's equal to 8 and 12. Now this one looks like a pretty easy one just to solve by elimination, right? So I think what I'll do is just subtract one of these equations from the other. 2x minus 2x is 0. 3x minus 3y minus 1y is 2y, and 12 minus 8 is 4. All right, so I get y is equal to 2. All right, so now we'll substitute it back into, let's substitute it into the second equation. 2x plus y, which is 2, is equal to 8. And so 2x is equal to 6 if I subtract 2 from both sides, divide both sides by 2, and I get x is equal to 3. So my intersection, All right, my intersection is 3, 2. Right, that's this point right here, 3, 2. All right, so remember my method of corners is just to evaluate the profit function at the corners, and that's where it's that if there's a solution to this, it's going to occur at one of the corners. All right, so we're going to apply the method of corners, which is on the next page, which I already went through. All right, so where are my corners? I have 4 corners. I have this quadrilateral. I have 4 corners. Now the value of the p of xy function at 0, when x is 0 and y is 0, then this function is just 0. So that's obviously not going to be the maximum. All right, so let's just move around the polygon here, and so let's take a look at 0, 4. What do I get if I plug those values into the profit function? So x is 0 and y is 4. Okay, so I get a profit of 8. All right, you might remember that from our little 3-dimensional demonstration. All right, let's take a look at the next one, 3, 2. Right, that's the next corner. So my profit function is 3 times x plus 2 times y, and when I get 9 plus 4 is 13. And then my last corner here is at 4, 0, and I get 3 times 4 plus 2 times 0 equals 12. All right, so those are all of my possible values. I just choose the biggest one because I wanted to maximize the p of x, y function, right? So this is my maximum. Okay. Now, when I write this, write my solution, I probably want to have, a little more description. And, in some of the word problems, it's a little easier. You kind of want to interpret your solution. You don't just want to say x equals whatever or p of x equals whatever. But in this case, I'm just going to say that I'm going to write a little more descriptive solution. So I'm just going to say that the profit function, this p of xy function, has a maximum of 13 when x equals 3 and y equals 2. Okay, so this particular solution didn't have any context around it. We don't really know what x and y represent, but so that's the solution to this to this linear programming problem. So just remember use the method of corners, right? We're just going to we're going to graph the feasible set and find the corners of the feasible set, and then evaluate those corners and choose the one that is that either maximizes or minimizes the objective function, whatever we're trying to do. Now there are some caveats to the method of corners. One of them is if we have 2 adjacent vertices that are the same, then essentially the objective function is going to be optimized all along that edge. Okay, so and if you visualize that the profit function constrained by the feasible set, it's really just it's just a polygon, right? And if one of the edges, if you have 2 edges that are at the same value, then every point on that edge is going to be the same value. So if one of those, if you have 2 adjacent vertices, or if the profit function is optimized at 2 adjacent vertices, then it's actually optimized all along that edge. Okay, we all have an example that includes that. And then we have some issues with unbounded feasible sets. Okay, and so in those cases, you might not have a maximum or a minimum, depending on the orientation of your objective function. Okay, so again, we might run into some of those cases here in some of the examples. All right, So, and I don't know, this one says that if the feasible set is empty, then you have no solution, which seems obvious to me. If you don't have any feasible values of x and y, then well, of course you're not going to have a solution. All right. Well, that's all I have on this example. I know that was kind of a long explanation, but I wanted to make sure that I wanted to at least give you a chance to try to understand what's going on here. And I will meet you in the next example.